Hey guys, welcome back. Now that we know what a minimum spanning tree is, we are going to focus on one of the famous ways to find out minimum spanning tree, and that's Prim's algorithm. Now let's recall what we will be given. We will be given an undirected graph. Every edge will be having some weight, some positive weight, and we'll have to find the minimum spanning tree in this graph. And for that, we are going to use Prim's algorithm. So let's talk about Prim's algorithm. Prim's algorithm is all about starting from a vertex in the given graph, then including it in the MST, and then expanding the tree by selecting more vertices one by one on the basis of minimum cost edge that's not yet included in the tree. So yes, it's kind of a greedy approach where we expand the tree greedily. Let's see, we start with vertex 0. We consider that it is present in the MST. Now from this MST or from this component, which right now is having only one node or one vertex, which is this vertex 0, we see all the edges coming out from this component. But don't forget, edges are not having any direction. Just for the sake of explaining it, I'm saying outwards. What I mean here is all the edges connected to, okay? And now from all these edges, we select the one with minimum weight. Or you can say with minimum cost or with minimum distance, depending on what kind of network or graph it is, okay? Now here, the one with minimum weight is this edge 0, 1 with weight 3. So we are going to select this one. On the other end, this edge is having vertex 1, so we're going to include this vertex 1 in the MST. Now this is the updated MST. So now we have to repeat the same for this updated MST or for this updated component. So again, we see the edges coming out from this component. We have an edge with weight 4, an edge with weight 2, an edge with weight 8. So these are the three edges that are coming out from 0 and 1, right? From this component. Again, we're gonna compare the edge weights. So the one with minimum edge weight is this edge 1, 3. So we're gonna include 3 in MST this time. So the MST or the component is now having 3 vertices, 0, 1, and 3. Again, see the edges coming out from this component. We are having one edge coming out from 0 towards 4. We are having one edge coming out from 1. We are having two edges coming out from 3, which are 3, 2, and 3, 4. So these are the 4 edges. Now again, let's look for the one with minimum weight, and it's the one with weight 4. So this time we are going to include vertex 2 in MST. Now there is one vertex which is still left to be included in MST. That's why we're going to repeat the process. So now the MST or the component is having 4 vertices, 0, 1, 2, 3. Let's see the edges coming out from this component. So we're having two edges, one with weight 8 and another with weight 11. Here notice that we're not considering this edge 2, 3 because both the vertices are already part of MST. So this edge is not going outwards from this MST. Now let's look for the minimum edge between these two edges that we're having. So the one with minimum weight is 0, 4. That's why we're going to go through 0, 4 and we're going to include this vertex 4. So this is the final MST with cost 17. Now let's understand how we are going to implement the same with pseudocode. So we are going to understand it from the instant where we are already having 3 vertices present in MST. So how the process starts? We loop over the vertices to see if a vertex is present in MST. If it's there in MST, then we go further and we again loop over all the vertices. and we find the adjacent vertices to this current vertex in hand. And that we do check by verifying that the vertex must not be already present in MST, because then it won't be an outward edge, right? And we also check that it must be connected to that already selected vertex. So if it satisfies all these conditions, all these two conditions, then the next thing is to choose it if the edge is a min-weight edge. So here, if I loop over all the vertices to find the adjacent vertex from this vertex 0, 1, we cannot select 1 because it's already there in MST. We cannot select 2 because it's not an adjacent vertex to 0. We cannot select 3, but we are going to select this 4 because it's adjacent to 0 and it's not present in MST. So the weight of the edge that connects 0 to 4, that connects 4 to 0 is 8. It gets compared with the previous minimum weight. The min variable starts with infinity, and as we keep finding a smaller value, we keep updating this variable. So here the weight of the edge is 8. We compare, is 8 smaller than infinity? Yes, it's smaller than infinity, so we update the value of min variable. So we iterated over all the vertices for this current vertex 0. Now the process gets repeated. It comes to 1. It checks if it is already present in MST. Yes, it's present in MST. So again, we loop over the vertices, all the vertices, to find out the adjacent vertices which are not present in MST. So the adjacent to 1 is 2, which is not there in MST. Now it compares the weight of this edge with the previous weight, with the previous min, which is 8. So it checks 4, is 4 smaller than 8? Yes, so it updates it with 4. Now 2 is not present in MST, so we're not going to go further from here. Next is 3. 3 is there in MST, so we loop over all the vertices to find out the adjacent vertices. 2 and 4 are adjacent to 3 and the weights are 10 and 11 respectively. So first for 2 it checks if 10 is smaller than 4. It's not smaller than 4, so it's not going to update the value of min variable. And then it checks for the next vertex. So the weight is 11. Again, it's not smaller than 4. That's why it's not going to update the value. So at the end of this iteration, this inner loop, again we are having 4 as the minimum weight. Now the last vertex. So it checks for 4 if it is present in MST. It's not there in MST, so it's not going to go forward. That's why after the end of this for loop, this outer for loop, the value that we're having in the min variable is 4, which belongs to this edge 1, 2. That's why we're going to include 2 in the minimum spanning tree. But the MST is still not complete. We are having this vertex 4 to be included in MST. So how many times we have to repeat this process to get the complete MST? For that we use this property which says the edges in a minimum spanning tree are exactly equal to the number of vertices minus 1. So until the edges are smaller than vertices minus 1, we are going to repeat this process so that at the end of this process we get all the vertices included in MST and we do have vertices minus 1 edges in the MST. So this is how we are going to implement it.